Okay. In the previous session, we talked about variational autoencoders, and we talk about ELBO. Today, we want to talk about that concept more and see how we can use ELBO to train a variational autoencoder. Okay, let's recap again what we have previously. We see that if for some applications, if you assume a high-level abstract representation or latent representation Z, which is itself a latent random variable or random vector, it's more easy to model what you observed condition on that latent. Okay? So if I have something latent, the distribution of what I observe condition on one of those latent variables is much simpler. We have the example of, for example, the gender, the age, or the pose. Then you can better imagine a face image with a given properties. Okay? So this model can help us to model complex distributions, and we see in the case of GMM how we can build how we can build complex distribution like this distribution, which is multimodal, using simple single mode and Gaussian distribution and a categorical distribution. And we see that as an extension to GMM is what we talk about in this presentation, variational autoencoders, where the Z variable is extended from a discrete random variable into a continuous random vector, and also the conditional, the previous conditional for the GMM is easily a selector using the Z, but here we pass the Z through two neural networks characterized with theta, and then the result generates the mean and the covariance matrix for the conditional distribution. So these are the differences between the GMM and variational autoencoder. So we start by this problem that to train the model, we need this value. We need this value as a function of parameters. So the most important point about the model is to calculate the unconditional likelihood of your data samples. So what happened here? This can be the integral of the joint, the integral over all possible latent of the joint, where you marginalize out the latent. It means that you calculate you have an observed data, you calculate what is the probability of the joint of your observed data and all the possible state for their hidden state, and sum them to some of them, so you have the probability of your data point. But what is the problem with this approach? But the integral is not tractable. Calculating this integral is not tractable. Why? Because you can write it as p theta of z times p theta of x given z dz. And you know that this is a normal and this is a normal, but the relation is that in this normal you have the mean and the covariance matrix are very complex function of z. So this relation makes it intractable, and we cannot simplify this relation because the flexibility of your model will be reduced. So we should think of alternative solution to calculate this integral. Okay. One approach to estimate this integral is to, again, assume this joint as the using chain rule as the conditional and prior over Z, you have this relation, and in this relation you have a very intuitive method to calculate the unconditional likelihood. It means that it is an expectation over the random variable coming from this distribution for this f function, f of z. We know that x is one of our data samples. It is not in this case we do not consider it as a random variable. Assume that it is one data sample. So it is expectation over z coming from the prior of this conditional. So we have a method, we have an expectation, and we know that I can estimate any expectation using Monte Carlo estimation. So I sample Zi from this distribution. So I sample Zi from this distribution and calculate these values. It is very easily you can easily calculate it and average over all resulting values. This is an approach to calculate the likelihood of one data point. What was the problem with this approach?
High variance.
Exactly, high variance. This approach gives you high variance. We see in the example of GMM here. These are the resulting values for the unconditional likelihood, and you see that 3 of them are almost 0. I forget to update this. This is minus 14. And also one of them which has a high probability give you high variance. So you have a problem with this approach. If ideally you were able to approach k to the infinity, everything works. But here we are not in that case. We want to give a practical approach to train the model. So we have something is missing here, and you cannot calculate the likelihood, the unconditional likelihood. So what was the alternative? We have an alternative for it. What was the idea?
Importance sampling.
What?
Importance sampling.
Yeah. Importance sampling. It means that instead of sampling from a prior distribution, have get some information from your data points. If I look at this integral, what can I do? I can divide and multiply the integrand with the function, with any function. So I add this distribution here, and it is easily equal to 1. So I can add it here, and I have this integral. So if I put the denominator here, again I have an expectation. I have an expectation of this more complex function than the previous one over a new distribution. So it is an expectation. I write it as here, but remember that it means that Z are coming from this distribution of the joint, your model joint, over the sampling distribution. This was an alternative. But there is another problem. How to select Q? What is the best Q? What was the best? We have one example that showed that something could be a possible Q. What was the possible Q, the suitable Q for our case?
Posterior.
The posterior of the latent given your data point. It means that assume Q of Z equals the posterior of the model, the current model with the parameter theta over the random, over the latent variable Z, given you are working with this data point. We see that how selecting this Q can solve the problem in an example. The example was again a Gaussian, a GMM, excuse me. This is a GMM. Here, I sample from the posterior, and we know that the posterior over the latent given the observed data for GMM can be easily calculated. And these are the values for the unconditional, for the data likelihood. You see here that the variance is is much more better than the previous one, and we can use it to train the model. Okay, but there was another problem, that this posterior over the latent given the observed data is not tractable for you for the real world application. Why? Because again, in the denominator you have the data likelihood, which is our objective to calculate. So for the real world, this is not an option. It seems that this is not an option because you cannot calculate it. This is the optimal, but you cannot calculate it. Okay, this is the problem. Okay, then we talk about the fact that we are looking to the likelihood of the data. We also call it the evidence. The likelihood of the logarithm of the likelihood, we call it the evidence. We are not looking for the likelihood, we are looking for the log likelihood. And the problem is that, assume that again we use importance sampling and assume that we are not, we can optimize this function over Q for the case of just talking about the ELBO. The log of this likelihood is the log of this expectation. We talk about two reasons that if we switch the order of these two operators, it means that the logarithm and the expectation, we get much more suitable terms for the learning progress. Okay, so we talk about two reasons. The first is that you to some extent separate or disentangle the factors which is a function of each of your variables. You know, here the Q and theta are the can be changed. You should optimize over them. And the second one was that you have to separate learning signals, and there are other reasons for this objective. But the challenge is that we know that the equality does not hold here because logarithm is a non-linear function. If it was linear, you can easily interchange the order of two linear functions, but a logarithm is not linear, so the equality is not an option, and you should find which of these hold. Maybe none of them, sometimes one of them, sometimes another. But we have an inequality named Jensen inequality that state that if you have a function which is a concave and you are evaluating the output of that function for an expectation, you can change the order by putting a greater or equal sign. It means that for our case, logarithm is a concave function, you have an expectation, so you can change the order and select this sign. And using the Jensen inequality, we reach the ELBO definition. The ELBO says that the evidence, we call it evidence, the evidence is greater or equal to the expectation of the log of this ratio. And this was the point we reached, I think, last session. So we have a notation for ELBO. You are talking about one point, you are talking about a model, you are talking about a sampling procedure. For all of them, you have a definition for ELBO. Okay?
Can you repeat it one more time?
You know, the ELBO here is a function of two parameters. It has a Q. By changing the Q, ELBO changes. Because it is both the sampling here and it is in the denominator here. Okay. Also, your model plays an important role in ELBO in the denominator here, because theta is your model parameter. Everything is around a data point x. We are not talking about more than one data point. We are just talking about one data point x. So the evidence about that data point or the log likelihood of that point is greater or equal than this expectation. And we see that this expectation can be easily calculated. Very easily and in a practical way. What happened? ELBO, you know, Z, why don't we have Z here? Can anyone tell about why we do not have Z here?
Because it's a latent variable.
It's latent, but we see Z in different terms. Why do not we have ELBO as a function of Z? Similar to X. Z is integrated out. You have an expectation over Z. That integral, observe all possible Z's and take the integral, and Z is integrated out. You do not have any dependency over Z. Okay? Okay. So this is our notation. ELBO, ELBO is something that you will hear about it frequently during this course, because the DDPM, the diffusion models also are built on exactly the same idea. So make sure that you understand everything about ELBO. It is very important in this course. If you have any question now, we can talk about ELBO. ELBO is clear? Okay. So what happened? I have the expectation of the logarithm so that the logarithm can divide the ratio of these likelihood into the logarithm of the likelihood. So I have this new formulation for the ELBO, and we talk that this term is the entropy of the distribution, Q. This is a definition in information theory. And we want to maximize the evidence or the log likelihood of the data. So instead of maximizing the data likelihood itself, we maximize the ELBO for that data point. Hopefully, maximizing the ELBO will maximize the evidence. Hopefully. Why? Because it is a lower bound. It just pushes the likelihood above and above, but you do not know where is the likelihood. What is the distance between the ELBO and the likelihood for the moment? Okay, so to understand how near we are to the likelihood using ELBO, we need to understand the tightness of ELBO. How tight is ELBO to the data likelihood? What is the distance between these two values? Okay. If we rewrite the KL divergence between the Q and the posterior of your model, we know that the KL divergence means that the expectation of the log ratio between these two distributions over the first distribution. So I write exactly the definition of KL here. If I work on the denominator here, I see that I have the joint over the data likelihood, and if I apply the logarithm on the numerator and denominator and separate them in this way, you have these three terms. The most important point is that the first term, because the integral of any distribution over the random variable is equal to 1, you have the evidence or log likelihood here. And there are also two other terms here. And if you pay attention to this definition, it is exactly what we see there. This is the expectation of the joint over the Q, and this is the entropy. So we find something that we need and that we look for. We want to know how tight is the ELBO. And we see here that the likelihood minus the ELBO equals the KL divergence between the Q and the posterior. The mismatch, we previously see that the posterior is a great option for calculating the likelihood. In the case of GMM, you remember, it makes it the variance is very reduced. Here we prove that the best option is the posterior. Why? Because it makes ELBO equal to your log likelihood, data log likelihood. And it's very interesting because you have a better control over the likelihood given the ELBO. Means by maximizing the ELBO with a small enough step, you are also maximizing the log likelihood if they touches each other or they are using the posterior of z given x for q.
Question.
Yes.
In the second last equation,
Here.
is it that the log is missing in the
Yes.
Yes.
Exactly. This is my problem. The log is missing here. Yes. Sorry. This log is missing here, and I will update it. Okay. Thank you very much. Okay. So we understand that the tightness of ELBO is the KL divergence between your Q, your sampling distribution, and the posterior of z given x. Okay. We said that as the distance between Q and P theta z in the sense of KL divergence increases, the ELBO becomes a less tight bound, and also if you have a matched sampling to your posterior, it means that ELBO touches the log likelihood. So for the matched case, we have that the log likelihood is equal to the L. This is a very interesting point. So we found the best option for Q, and it seems that everything is solved. But we have another challenge. What is the challenge? The challenge is that the posterior is not tractable. We talk about that the posterior is not tractable. So you want Q to be something which is not tractable. And this is the new problem. So the previous challenge was solved. The best option for Q, we understand that the best option is the posterior. P theta of z given x is the best option for the ELBO, which in this point the ELBO touches the likelihood, the log likelihood, but the problem is that the posterior is not tractable. So you cannot minimize this distance. You can think that, so I optimize the KL over Q, but you do not have the right distribution to optimize this KL. We have another problem, and we should solve this new problem. So now we want to tighten ELBO. What does it mean? We know that we cannot optimize Q using by minimizing this loss to some extent, but we want to find another way to tighten ELBO. This problem, minimizing KL over Q, is ELBO tightening, but it is not tractable. We want something tractable to optimize, to tighten ELBO to the true log life. So to approach this objective, first we parameterize Q. Instead of considering all possible functions, we parameterize Q in our objective is that we optimize these parameters instead of looking in the set of all possible distributions to tighten ELBO. It means that instead of minimization over functions, now we minimize over the parameters of a selected family. We simplify the problem. Instead of minimizing over all possible functions here, all possible continuous distribution PDFs, we here select one PDF, which is Gaussian here, and then optimize the parameters of that Gaussian. It means that we impose some restriction, just Gaussian, nothing more. And then we optimize the parameters of that Gaussian such that the ELBO is tightened. Okay? So instead of optimizing over functions, over PDFs, possible PDFs Q, we optimize over the parameters of a Gaussian. We select the Gaussian as the function, the base function, and then optimize its parameters. Okay? Everything is clear? So assume that Q is a normal distribution. It means that you want to find the nearest normal distribution to the posterior. We do not know how. We know that we cannot implicitly, we cannot directly minimize the KL divergence between Q and the posterior, but we are looking for some methods so that we can minimize this distance. Okay. One important point that I want to emphasize that we are just talking about one data point, X. We are not talking about the data set, okay? Pay attention to this point. We are just talking about one data point and want to maximize the likelihood of that data point. Then we can easily extend it to the whole data set. For the current, we just pay attention to one data point. It means that the design Q is just for that data point, you know? It is not suitable for other data points. Why? Because the posterior of a Z given X will change if you have another data point. For the current moment, we are just focused on one data point, and that data point we want to design the distribution for one sample of your data set. It is very important to understand this point. Okay, we changed the ELBO. ELBO was previously denoted as ELBO of X with theta and Q. The Q is all PDFs, all continuous PDFs. Now we have lambda here. Lambda are the parameters of the Gaussian distribution. So the dependency of the ELBO over the sampling distribution is via this lambda vector. Here the lambda is a mean, and the variance and the covariance matrix is diagonal with that variance. Okay. Everything is clear? We have a new definition for ELBO, not new definition, new notation for ELBO. Again, everything is about X, nothing more. It means that if you find lambda, that lambda is suitable for that X, not the other X. Yes?
Please go back to the previous slide. So previously we didn't have Z in the ELBO because it was integrated out.
Yes.
But now we have Z in a way because we have lambda, right?
No, again, if you write the definition of this expectation, you see that the Z is integrated out. Because you are expecting the whole function over all possible Z, and you have a dZ in the expectation, you mean? You understand? Just X will remain, and also the theta and the lambda, which are the parameters. If you change lambda, it means that you are changing the sampling, and it will certainly affect the ELBO, because the sampling is changed and also the denominator is changed, both of them. The dependencies over lambda is very complicated, and we see that one of the other challenges is this dependency. You are sampling with respect to a distribution that its parameters are your parameters, and you should optimize them. It is very complicated.
So since it's specific to X, then is that like challenge 5 or?
Yes, that's the challenge. Another challenge, you know. The scalability will be difficult, because for each data point you have one distribution. For each data point, Q changes. Here we are talking about just one X. If you design lambda, that lambda is suitable for your X, not the other X. If you go through your distribution, your data set, you have other X's, so you should design new lambdas. Yeah. And it makes the method not scalable for the large data set. We will see that how we can solve that challenge. Yeah. That's also another challenge. So let's think of the direct problem. If we can minimize this KL divergence over all acceptable parameters for your Gaussian distribution, then you will have the tightest elbow. That elbow will not touches your likelihood, your log likelihood. Why? Even you find the best lambda here, why it does not touches your log likelihood? Yes, because you restrict the Q to the Gaussian. If Q was not restricted and you can select all possible distributions, then if you can solve this minimization problem, you will find the best option, and then that touches elbow, that touches the log likelihood. But here, because you restrict the Q over the Gaussian, restrict to the Gaussian, it means that even you find the best option, that best option is not the option that the elbow touches the log likelihood. But it is tighter than randomly selecting parameters. Okay? You cannot touch the log likelihood. Yes?
Is Q often chosen to be Gaussian?
That's due to some simplifications in the final optimization problem, because at the end you have a distance between the KL distance between two Gaussians. If you select elbow something else, that distance will be very difficult to calculate. You will see it. Elbow is a great option here. Gaussian is a great option because of the implementation notes. So, if you can find another point is that if you optimize this KL, if you minimize this KL with respect to lambda, that lambda is just related to the current model. It means that if you change the model, that lambda is not the best option. Why? Because if the model is changed, the posterior over z given x is changed. Okay? If the model is changed, this value is changed. Every model gives different posterior to your latent. So if you change your model, the lambda is not optimized anymore. So this lambda star is a function of theta 2. Again, pay attention to this point. You can think of it, and we can talk about it. You should think of the model. You have a model. This model have a likelihood. For example, this is the likelihood of your model. If you change it means that for any point, if you are at this point, your elbow is something, for example, like this. We know that elbow is lower than your likelihood at this point. If you maximize that KL, it means that you come from this form to something like this. This is the previous one, this is the new one, and this is tighter. This is the previous, and this is the new. But everything is about this point, which has this posterior over the latent. If you change theta, you come to this point. The posterior over the latent given the x, even x is fixed, will be changed. And using the Q you have previously designed is not the optimum here. Maybe it's in this point, and if you update your likelihood, your lambda, you have a tighter elbow. So pay attention to the point that lambda star is a function of your model, your current model. If you change the model, lambda is not the lambda star, it is the lambda. So the optimization is intractable because you have not access to the model posterior. But pay attention to the functional form. Pay attention to this function. The left-hand side is not a function of lambda. Data likelihood is not dependent on your sampling procedure. The right-hand side is a function of lambda. What does it mean? How we can use this feature? These two terms are function of lambda, we know. This term is not a function of lambda. If you increase this term with respect to lambda, what happened to this term? Exactly, it will be increased. Again, because the summation of these two terms with respect to lambda should be fixed. Why? Because the left-hand side is irrespective of lambda. It is not dependent on lambda. If you change lambda, just these two terms change, but the summation should be fixed. What does it mean? If you maximize the ELBO with respect to lambda, you are indirectly minimizing the KL with respect to lambda. Is it clear?
So you can ignore.
What?
So does that mean like you can just focus on the ELBO?
Exactly, yes. It is not needed to focus on this KL to tighten ELBO. If you maximize ELBO with respect to lambda, you are indirectly minimizing the KL divergence between the Q and the P, the posterior over Z. Your model posterior over Z given X. It is clear why we can maximize ELBO instead of minimizing the KL between Q lambda Z and P theta Z given X. If you change lambda, the left-hand side is fixed. If you maximize ELBO with respect to lambda, it necessarily minimizes KL with respect to lambda. And this is our objective, minimizing the KL with respect to lambda. It means that we are tightening ELBO. Clear? Okay. This is the most important point about how to select this in sampling procedure. LHS is independent of lambda. Both terms on RHS are function of lambda. How we can decrease the KL divergence? Here. Because it is independent of lambda, if you maximize ELBO with respect to lambda, it means that you are minimizing the KL divergence with respect to lambda, and this relation will hold. So, to tighten ELBO, you can maximize it with respect to lambda. We find the solution for the new challenge. The new challenge was that you cannot make the KL distance between the Q and the posterior, you cannot minimize it. Why? Because you do not have access to the posterior. Posterior is intractable. But here we see that if you maximize ELBO with respect to lambda, it is equivalent to minimizing that KL, or equivalent to tightening the ELBO. Clear? Yes.
I'm a bit lost. So do you still have different lambdas for different x's?
Exactly. We are talking about one x now, nothing more. Just one data sample. Everything here is about one data sample.
So even if we get the argmax of ELBO, what happens during inferencing then? Because that would be like a totally new.
Yes. The problem with this approach is that in the inference, you should first optimize the ELBO with respect to lambda, and then calculate your model posterior. Yeah, model likelihood, yes. Not model likelihood, the ELBO. It means that the lower bound to your likelihood. It is very limiting. It seems it will, you said that, assume that I have a trained variational autoencoder. It means that I have theta. For a new data sample X new, what happens? First, you should find the lambda star corresponding to this new data point. It is an optimization. It is very hard. It means that for the inference time, you should first optimize something and then use that lambda star to find the value of ELBO for your x new. The model is trained, so you do not need to train the model and this lambda star. Then just you have a lower bound on the likelihood of that data point, not even the likelihood of that data point, you know? And yeah, this is the problem, and it can be solved via amortization. You will see that there is a technique named amortization. In amortization, in the inference time, it is not needed to optimize over lambda. Yeah, that can be solved. Okay, any question about the ELBO tightening? Yes.
So the formula that you wrote, like the last formula, this is basically following your discussion. This is for the inference time because you have the fixed model theta, and you just want to find the lambda that maximizes that ELBO.
For the current problem, it is both for the inference and training. Assume I am in the training. I want to maximize the likelihood of data set. Focus on one sample of the data set. I want to maximize the likelihood of that sample, change the model so that I cannot maximize the log likelihood because it is intractable. Instead, I want to maximize ELBO. Before maximizing ELBO, I maximize ELBO with respect to lambda so that I have the best ELBO, then maximize the ELBO with respect to the model parameters. And that makes sense. You first tighten it, then
maximize it, yes.
Everything is clear? Okay, let's continue. This is an example of ELBO tightening. If we have time, it is a great example to understand how maximizing ELBO with respect to lambda. Yeah, okay, we can talk about it. Okay, let's start with an example. Pay attention to these examples. If you understand it very well, it means that you can extend your understanding to the case of variational autoencoder. It is a GMM. We want to talk about the ELBO and the tightening for a GMM. GMM, we know that GMM is a special case of variational autoencoder to some extent. The Z variable is discrete. The conditional is selector. It means that the distribution over X given Z is a normal with mu Z and sigma Z. The role of Z is just to select the mean and covariance matrix. So let's talk about the GMM. For the GMM case, the most important point is that everything we assume intractable is tractable. Why? Because Z is just a limited number of cases. For the case of showing, for example, how the summation of ELBO with the KL is equal to the log likelihood, we calculate these marginal likelihood, but in the real world case, we cannot calculate them. We here just to show that the equality we talk about, we calculate the log likelihood, the unconditional likelihood. Assume I have a GMM, because previously, for the case of continuous Z, I cannot calculate this integral because Z was a normal. But here, Z is continuous. It means that to marginalize out Z, I should sum over all possible Z. And here I have 2Z. Assume that I have this case. A sample where I have just 2 groups of data, and I know a priori that the number of the groups is 2. It is given to me. This is a very simple case, but we just want to have intuition about elbow and elbow tightening. Okay. So, although in the general case this integral is not tractable, for our case it is easily we can easily calculate the data likelihood. We know that it is the summation of joint over x and the random variable z equal to z. And this joint is easily factorized as these two terms, and both of them can be easily calculated. This is the prior over z. In GMM we show this value with pi. Pi is the categorical distribution parameters, and for z it is pi of z, because this z should be lowercase z, not uppercase. And also the conditional distribution is easily a selector based on z. So for any x, if you give me an x, I can put it inside the normal distribution with noun mean, with noun covariance matrix. It gives me a number. Here also I have a probability of z equal to z to lowercase z. It is also a number between 0 and 1. And then I multiply them and sum over all possible z, which here are 2 possible z, and can calculate the likelihood for a data point. Okay. So here we assume that the model parameters are given. In this example, we want to show this relation. If you maximize elbow with respect to lambda, you are at the same time minimizing the KL with respect to lambda. Because of the GMM case, you can easily calculate both the elbow and the KL. Why? Because the posterior over z given x for the GMM can be easily calculated. Why? Because P of x is previously calculated. The problem with the posterior was calculating this value, and here we can easily calculate this likelihood. Okay, let's talk about each of these problems separately. First, we want to minimize the KL divergence between Q lambda z and P theta of z given x. Because z is binary, 0 or 1, Q lambda z, the general case, the most general case for the Q is the Bernoulli distribution over z with one parameter lambda. So instead of the variational Autoencoder where lambda was the mean and the sigma 2, here you just have one number between 0 and 1, which is the Bernoulli parameter for z in the Q distribution. Also, the P theta of z given x is again a Bernoulli distribution, which the parameter is a function of your model parameters. Your model parameters are this set. Given all of them, you can easily calculate the posterior. How? How can I calculate? Assume that I want to calculate the parameter. That parameter, you know that the parameter of the Bernoulli distribution is the probability of z equal 1 given x. So how can I calculate this probability? It is easily calculated using Bayes' rule. It is the probability of x for z equal to 1 times the probability of z equal to 1 over the unconditional data likelihood. So I can assume z equal 1. It means that mu 1, sigma 1. Then put the x inside the normal distribution, the resulting normal distribution, and this number is generated. Then p theta z equal 1 is also p1, and the denominator is calculated above. So I can calculate this value, and this probability is beta theta, written here. Because beta theta for a Bernoulli distribution is the probability of z equal to 1, and here we can calculate it. So for the case of the GMM, both of them can be easily calculated. The upper one is changing because you want to select the best lambda. The second one is fixed because the model is fixed. And to emphasize that we are just working on one model, we write it as beta of theta. It means that for this model, that is the posterior is the Bernoulli you calculate here. For if you change beta, theta, everything will be changed. So, what is the optimum lambda for the RSH? The optimum lambda is the one that result into the nearest minimum distance between these two distributions. And you know that they are both Bernoulli, so if the lambda equals beta of theta, it means that both distributions are equal and the KL divergence is 0. So the best option here is lambda star equal to beta of theta. And we can find the beta of theta for GNM. We can calculate it as you see here. So we find the left-hand side, or maybe we find this part, the right-hand side of this object. Now we want to focus on elbow. So yes, here. Oh, sorry. All these calculations are here. I forget it. The probability of your model for z equal to 1, which is the beta of theta, the first step is the Bayes rule. The second step is marginalization. You marginalize out the joint in the denominator, and you know that this joint is the multiplication of these two factors using conditioning, and this is the lambda star. You know that all the parameters of the model, lambda 1, sigma 1, p1, p0, sigma 0, lambda 0, all of them are known. You have a model. You have a trained model. So I can easily calculate lambda star using this procedure. And this is an example. You have a model. All of them are given to you. Using these equations, I can calculate the lambda star, which is 0.76. So then using, all right, it means something is missing here, I think. This is the data point. This is the component number 1. This is the component number 0. And you calculate that the posterior, your model posterior for z equal 1, given x, given that's x, is equal to 0.76. It means that your model, your current model, assume higher probability for this data point to be associated with the component number 1. Because this is the probability of 1. It is visually intuitive. Why? Because this group has a wider variance and it can better capture these points, although it is nearer to the mode of the other components. But it has a higher variance, so it can better capture it. Okay? So here, for this problem, I can calculate the posterior, I can calculate the best Q lambda. Now we want to optimize the LHS. It means that we want to maximize the elbow with respect to lambda, and hopefully we should see that lambda equal to 0.76 is the best option. Again, similar to the previous one. We know that elbow is the expectation over the z coming from this distribution of this logarithm. So, but the expectation over a binary random variable is very easy. It is equal to the logarithm, this function for z equal to 1 times the q lambda of 1 plus the value of this function for the z equal to 0 times the q lambda 0. This is the definition of the expectation. But because the random variable is binary, it has just two terms. Okay? P theta of x, the joint P theta of x and 1 can be calculated using conditioning, as here. It equals to P theta of x given z times P theta of z equal 1. The denominator PQ lambda of 1. We know that this is a distribution with lambda parameter. It means that the probability of z equal to 1 is lambda. I put it here. And also the Q lambda of 1 here is also lambda. If you calculate all of them, you have a function of lambda. You have ELBO as a function of lambda. You are in one data point. You are in one model, theta. So you have just a function of lambda here. Assuming fixed, we can, assuming the situation I mentioned before, for a fixed x, for a fixed model, you have a function of lambda and you can plot it. Here also, so here I calculate the ELBO as a function of lambda. ELBO as a function of lambda. Here I want to calculate the KL divergence between the Q and the posterior as a function of lambda again. Why? Because the second one is fixed, because the model is fixed, the x is fixed. Just the thing that changed in this KL is the parameter of your sampling distribution. So again, because you have a KL over a binary random variable, you have just two terms in this expectation. I write down both of them, and the resulting is this function. This is the KL as a function of lambda again. Also, we previously calculated the data likelihood, and this is the curve. What is this curve? I calculate the data likelihood in the first slide of this example. I just plot the logarithm of that value here, and it is fixed. It is not changing based on lambda. This is exactly the left-hand side. We said that the left-hand side is independent of lambda. This is independent of lambda. The blue curve is ELBO. The blue curve is ELBO as a function of lambda. We see how you can calculate ELBO as a function of lambda, the blue curve. The green curve is a KL divergence between the Q and the posterior. And you see that for the option we found before, the ELBO touches the evidence or the log likelihood. Equivalently, the distance equals 0. As we expect. It means that maximizing ELBO equal to minimizing the KL divergence. This is for the most simplest case, but it can be easily extended to the general case of variational autoencoding. Instead of minimizing the KL, which is not tractable in the real world application because you do not have access to the posterior, we can maximize the ELBO. And in the best point of in the global maximizer of your ELBO, you have the global minimizer of your KL divergence. So first, you come here, you come to the point that touches each other, these two. Then you maximize theta. Why? Because you want to maximize the likelihood. Yes?
Is K always a convex functions?
What? It's dependent on your on the way you formulate your distributions. Yeah, because assume that they are both distribution of the same functions, then it can be convex. For example, one modal Gaussians, you know.
But ELBO is always concave, right?
No. It is very complicated. It is very complicated, and the log likelihood, the data likelihood is very complex because of the form. The ELBO is very dependent on the selection of the parameterization of the Q and the posterior, how you parameterize the Q. If you parameterize it in a simpler way, you may have some cases such as this one, where the elbow is concave. But in the general case, it is not the case. Yeah. This is just very, very simple visualization. In the general case, everything will be changed.
Because I was thinking, if you maximizing the elbow and minimizing the KL, right?
Yeah.
So if KL is convex and then elbow is concave, then
yeah, that's the
maximizing.
But pay attention to the point that their summation is independent of lambda. It means that irrespective of the form, if you maximize the elbow, you should minimize the KL, irrespective of whether they are concave, convex, anything. Yes?
Does that mean that's a local minimal?
Hopefully, in the case of variational autoencoder, we just have one gradient step to maximize the elbow with respect to lambda. It means that we do not solve it until to find a global or local maximum of the elbow with respect to lambda. We just have one step because the curve is very complex with respect to lambda. It is not simple. In the general case, I mean, not here. Any question? So, I think now we completely understand how maximizing elbow is equivalent to minimizing the KL divergence between Q and posterior over Z given X. So let's summarize everything we talked about and the challenges we have solved till now. Starting from to calculating the data likelihood, we see that this integral is not tractable. You cannot calculate it in closed form. The first solution was to recast it as an expectation. We see that as an expectation, it can be the expectation of the conditional of your observed data given the latent over the latent coming from the prior, but this approach has a high variance, so we cannot use the Monte Carlo estimation to estimate the result, the data likelihood. The solution was to use importance sampling. We see that the data likelihood can be written as the expectation with an arbitrary QZ of this function. The problem with this approach was that you cannot select Q very easily, and the best Q cannot be calculated easily. So we change this form here because we are working on the logarithm of this likelihood to an elbow. The elbow is a upper bound to the logarithm of this term. It's a lower bound to the logarithm of this term. And we see that using elbow, the best option for Q is the posterior over Z given X. But the challenge was that although this is the best option, calculating the posterior is not tractable. So we should, instead of minimizing this KL divergence, we can maximize the elbow with respect to the lambda. So at the end, we are at this point. We want to maximize the elbow with respect to lambda. Okay? The new challenge. The new challenge is that we want to maximize elbow with respect to lambda and also the model. Why? Because we want to maximize the likelihood. And maximizing the likelihood means that we should maximize the lower bound on the likelihood. So we need to calculate the gradient of elbow with respect to both the model parameters and your sampling parameters. And this is the new challenge, how we can calculate the elbow gradients. So starting with the gradient with respect to the model parameters, which is very simple, assume that I want to calculate this gradient is the gradient of an expectation. I just write down the definition for ELBO here. This is an expectation over this, the logarithm of this, the difference of these likelihoods. And we know that because both of them are linear, you can change the order of the expectation and the gradient. The most important point is that the sampling is not dependent on your theta. It means that you can change it. If the sampling was a function of theta, you cannot change them because sampling is not, expectation with sampling is not linear with respect to the theta. But here, because you do not have theta in the sampling distribution, you can change the order, and everything now can be easily calculated. You know, the gradient of these two, the minus of these log likelihoods. The second one is irrespective of your model parameters, so it can be omitted. You just have the first one, and you have an expectation of gradient of a function. How you can calculate it? As always, Monte Carlo estimation. You have expectation of something. Instead of calculating the expectation, sample from distribution, calculate that function, average over all possible, average over all calculated values here. So I can calculate the grade, I can estimate the gradient with respect to the model parameters easily by just sampling from the Q distribution. These are the explanation about these equalities. Okay, the next one is sampling with respect to the sampling parameters. The gradient of ELBO with respect to lambda is the gradient of this term with respect to lambda, and now you cannot change the order. Why? Yeah, lambda is a parameter of the sampling procedure, and you cannot change it because you do not know how they are related inside that function. And this is the new problem. This is the new challenge, and you should solve this challenge. Okay. So the challenge number 5 was that you cannot minimize the scale directly because you do not have access to the posterior. We see that instead we can maximize ELBO, but the new challenge is that to maximize ELBO with respect to this lambda, you need a gradient. And calculating this gradient is not easy. Let's just talk about the idea, and then we can finish this session. I want to take the gradient of the ELBO with respect to lambda. For this purpose, I apply two approximations, two limitations. The first is that we again assume that the Q is a normal distribution with mean mu and the covariance matrix equal to I. So it has just two sets of parameters. One of them is a vector, the other one is the scalar. If you want to sample from this Q lambda z with these parameters, it is equivalent to sample from a normal distribution and then using this transformation generate z. What happened here? If you know that any linear function of the normal distribution is again normal, and if you calculate the expectation and the covariance of this new random variable, you can easily see that the resulting z distribution is again similar to what you want in your sampling procedure. So instead of sampling from z, I can sample from this standard normal distribution, and then instead of z in my function, use the mu plus sigma epsilon. This is, assume that this is function. The z calculating in this way is normal. We have one line here, one vertical line. The normal over z between mu and the covariance matrix sigma to I, which is your Q lambda z. So I can rewrite what I intended to calculate in this way. What changed? Instead of expectation with respect to z, I am expecting with respect to epsilon, which is a normal distribution, which has a normal distribution. And instead of using z here, I use g epsilon and lambda. G epsilon and lambda is defined here. An affine transformation over the epsilon. Very simple. Okay? What happened here? How it can solve my problem? Now, the expectation is not related to the parameters. The expectation do not have any parameters. It is a standard Gaussian. So you can easily change the order of gradient with expectation. What happened instead of using z, you use mu plus epsilon, sigma times epsilon. So the role of the sampling parameters go inside your functions. And then you take the gradient and calculate the gradient with respect to lambda. So you change the order, and then you have an expectation of something. Again, Monte Carlo estimation. You have expectation of something. You can sample from easily distribution, standard normal distribution, and then calculate the value of what is inside the expectation, which is a gradient. And the result is the gradient of ELBO with respect to the Q parameters. And in this way, you can calculate both the gradient of ELBO with respect to theta and lambda. And we have a great image here. This image can easily show something about what happened in the ELBO. Okay, we can stop here. Just remember that how we change the procedure here to be able to change the order of gradient and expectation, and then we can easily use the Monte Carlo estimation. In the previous part, because they cannot be changed, because this sampling was a function of the lambda, we stop here. There are also other options to solve this gradient, but the one that we will talk about in this course is something which is called reparameterization trick, as you see here. Thank you very much. If you have any questions, we can talk about it.